So you may have noticed in previous lessons in this unit, all of the examples we've been working with are situations where we know the charge on each of the ions. Either we can predict it from the family on the periodic table, or we're dealing with polyatomic ions that just have the charge that they have and it's given to you. But we know from the last unit that there are some situations where we can't predict the charge because there are multiple options, and mostly that applies to the transition metals. So because they have, or can have, because transition metals can have multiple possible charges, we need a way to specify when we're naming a compound which charge we're actually talking about. So, for instance, if I asked you to write the formula for iron oxide, you couldn't do it because iron can have multiple possible charges. So there are multiple different ways that iron and oxygen can combine. If using the naming system that we've built up so far, there are multiple different compounds that you would want to refer to as iron oxide. And in chemistry, that's not okay. Every compound needs a unique name. So we need to add one last piece to our naming of ionic compounds in order to kind of make it complete. So when we're dealing with a transition metal, and only when we're dealing with a transition metal or another ion that can have multiple possible charges. So we mentioned that tin and lead can also have multiple possible charges, either +2 or +4. So everything we're talking about with transition metals today, we treat those metals like transition metals as well, because functionally they're the same in terms of how we need to name those compounds. So we need to add a piece to our name, and what we do is we use a Roman numeral to specify the charge on the cation. So, quick refresher of our Roman numerals. 1 is I, 2 is II, so on and so forth. 4, 5 is V, 6 is VI, 8 is realistically as far as you should ever need, but we'll go to 10 just in case. So we use the Roman numeral to specify the charge on the cation. Note that this will never happen with anions, so we don't need to worry about what do we do if there's an uncertain charge on an anion. It just so happens that all things that form negative ions only have one option. So this only applies to our positive ions. So for instance, if I wanted you to write the formula for a specific version of iron oxide, I might ask you for iron 2 oxide. So what this is telling you, this Roman numeral 2, is telling you that it is Fe2+. Most important thing to remember is that the Roman numeral is specifying the charge. A really common mistake I see people make is that they want the Roman numeral to be the subscript, and that is rarely going to be the case. Very occasionally, by luck, it works out that way, but not most of the time. So what the Roman numeral is telling you is the charge on the cation. It's telling you that it is Fe2+. And then oxide, we know oxygen being in group 6A likes to form ions with a -2 charge. So when these two things combine, we have 2 positives and 2 negatives. That adds to 0 as is. So that is going to be in a 1-to-1 ratio. Another version of iron oxide that exists is iron 3 oxide. So why don't you take a moment, pause here, and try to write the formula for iron 3 oxide on your own. So again, that Roman numeral is telling us the charge. So iron 3 is telling us that this is Fe3+. Oxide is still O2-. So in this case, our charges don't add to 0 as is, so we're going to have to adjust some subscripts to make it so that we have an equal number of positive and negative charges. And the simplest way we can do that is to have 2 of our iron and 3 of our oxygen. So we end up with 2 times +3 is +6, and then 3 times -2 is -6. So those balance each other out. If we want to come up with the name, if we're given a formula that we need to produce a name for, we need to figure out what the charge is to determine what Roman numeral we should include. So for instance, let's do CuSO4. So for this one, we've got a polyatomic ion involved. If you consult your list on the back of the periodic table, you will find that the charge on a sulfate ion is -2. And if we're given the formula, we know that the charges have to add to 0, and the copper and the sulfate are present in a 1-to-1 ratio. So if the copper is -2, sorry, say that again, if the sulfate is -2, then the copper must be +2 to balance it out. So we can use the formula, if we're given that, to determine the charge on the cation, and then use that to name our compound. So since the charge on that copper ion is 2, is 2+, we would call this copper 2 sulfate. Let's do one more. CrNO3 3. So take a moment, pause here, and give this one a try on your own. So once again, we have a polyatomic ion involved that we're going to need to go look up. So we have the nitrate ion here, which has a -1 charge on it, but we have 3 of them. So that means we have a total of -3 charge on all of our anions put together. So in order for this formula to add up to 0, the charge on my chromium must be +3. So when I name this compound, I'm going to use the Roman numeral 3 to indicate the charge on the chromium. So this would be chromium 3 nitrate. So by adding that one extra piece of the Roman numeral into our name, it helps us specify which exact version of the compound we're talking about when there are multiple possible charges for things like transition metals, tin, and lead.